right now.
Okay, so remember Unit 6, Inference for Categorical Data, is all about just proportions this unit. We're going to talk about other ones in other units. Everything we did before winter break is your high school stats. Okay, everything we're doing now to the end of the year, more like till the end of spring break, so that's when we're going to finish, is going to be your college stats. Okay, not to say it's harder. Okay, we're just going to talk about a little bit of different formulas. So these notes 1 is about confidence interval for a population of proportions. So let's talk a little bit about confidence intervals. If we want to estimate the value of a parameter, which we know is P, from a population, we can take a sample and use our sample statistic, which is P hat, to estimate P. So if we think back to the simulation, P, the parameter, was that 0.7, what the actual value of check marks. Okay, our statistics P hat is what your class got after doing the simulation, which was about 0.65. It says we know that selecting different samples will yield different values of P hat, and we will therefore get a different estimate of P each time. So what this means is I did this 3 times in my 3 different periods, and we all got a different P hat value, which means when we were trying to estimate P, all of us were a little off. We were not exact. Because of this, instead of giving a single estimate for P, we give an interval of plausible values for the population parameter using P hat. So before, when we did our simulation, we said, okay, this was our estimate, that one P hat value. Now when we're doing confidence intervals, we're going to create an interval and say within this interval is all the possible values. Okay. A confidence interval is an interval of plausible values, so repeating what we just said above, for an unknown parameter. Okay, we need a confidence interval in order to estimate P. Okay, we don't know P. For a population proportion P, we can estimate its value using P hat as our point estimate. And construct a margin of error around it. A margin of error is constructed with a degree of confidence in the standard deviation of the sampling distribution. The confidence level describes how confident we are that the interval captures P. Okay, so the formula for this is the point estimate plus or minus the margin of error. So how this looks like is we can see it in several ways. We could see this as the point estimate, let's say 0.55, plus or minus the margin of error, let's say 0.15. You could also see this as 0.4 to 0.7. So these two things are the exact same thing. What the second interval is showing is that they already added and subtracted the 0.15 from 0.55. That's how they got 0.4 and 0.7. Another way is to show it as 0.4 to 0.7, like in words. So I would say this first one here is great if they are just asking for a quick point estimate and margin of error. Okay. This one is best in an FRQ where they're asking specifically for a confidence interval. And then this one is best when you write your conclusion in an FRQ. But they all mean the same thing. Ideally, if you want the full points. Okay, confidence levels. So the confidence level is generally described as C with a percent sign. where C represents the area between two z-scores that we call critical values. Okay, so no longer will we call them z-scores. We will call them critical values. They're the same thing. A critical value is the z-score that sets the boundary for our confidence interval. It is labeled as Z star. Okay, this is where you're going to need your Chromebook out, so make sure you're on Desmos. And then I'm going to write the steps so you have the Desmos steps. Okay, so I suggest that you either cross it out, cover it with the sticky note, that's up to you. I am going to, because I am on technology, I am going to erase this part so I can use this. Okay, so again, we're not using the TI-84, we are using Desmos. So the steps to find Z star on Desmos would be to first go to add an inference. So it's that plus sign off to the side. Then you're going to hit probability distributions. And you are going to select a standard normal distribution where mean is 0 and standard deviation is 1. Then you're going to click on bounds and type in your area as a decimal. So your area is always going to be that confidence level. So if they say we are 99% confident, that means the area is 99%, which we write as 0.99. And then lastly, we need to remember that for Z star, we only want the positive value. They're going to give you both because it's a boundary. So you're going to get the negative and the positive one, but we only want the positive one. Okay. Let you guys copy that down, and then we're going to use the next 4 examples. I'm going to show you how to do it on Desmos.
What's area as?
Decimal. Area as decimal. I ran out of space. Okay, so let's go ahead and look at the 80% one first. So I'm going to pull up Desmos. Okay, so on Desmos, the first thing you're going to do is add an inference. So that's that plus sign. So we're going to click on the plus sign. You're going to go to inference. And then you're going to click on probability distribution. And it's going to automatically set you to normal distribution. You just need to remember that we're using standard normal. So our mean is 0 and our standard deviation is 1. You hit create distribution and you're going to get a standard normal curve. You're going to hit that drop down where we can see the regions and the area and bounds. We don't need to worry about the regions. We just need to click on bounds. And then at the end, we're going to type in our area, and our area is our confidence. So since our confidence is 80%, what am I going to type? 0.8. And then notice it gave me 2 values, a negative value and a positive value. Which one am I going to keep? The positive value. So on your paper, what you're going to do is you're first going to draw a sketch of that interval. It doesn't need to be perfect. Okay, here is my negative. Need to make this a little smaller. Okay, this is my negative Z star value. This is my positive Z star value. Everything in between here is 80%. And if you look at Desmos, it even shows it for you. So technically you could just copy down that picture. And then everything in between. That is our area. Once we have our picture, we can just write what Z star is. And we found that Z star is 1.282.
Did we put plus or minus or no?
No, it's always positive. Okay, so go ahead and take a minute and do the next one. Once you're done copying this down. And if you finish that one fast, go ahead and do the last two. What you'll notice as you're working through these is that you're getting the same answer as everyone around you, which means the Z star value or the critical value doesn't change when you change, it doesn't change when you do this multiple times. The 80% confidence will always have a Z star value of 1.282. Okay, which means if you wanted, you could just memorize the most common confidence levels and memorize the corresponding Z star values with it. And you don't have to because you have access to Desmos, but it could save you time. Okay, so while you guys are working on that, I'm going to go ahead and just draw my diagrams. And it's just as simple as this, drawing the standard normal, creating the middle to be your confidence level, highlighting that middle space to represent the area, labeling negative Z star, positive Z star. Because remember, Z star represents our boundary for our confidence interval. Yes. Mm-hmm. Ideally, when you're drawing them, you want to make sure that they're not like all exactly the same, right? Because a 99% confidence should be a larger area than, let's say, an 80% confidence. That's the only thing I would be careful on. Okay, so for the 90% confidence, you guys should have got that Z star is equal to 1.645. Everyone get that? For the 95%, you should have got Z star is equal to 1.96. And then lastly, on the 99%, you got Z star is equal to 2.576. So what do you notice about the Z star values as the confidence increases? The Z star increases, right? So that would be something important to remember, that correlation. As the confidence level increases, your critical values increase. That could be a multiple choice question.
So
They're directly proportional. Mm-hmm. Okay. When you're done with this, you don't need Desmos anymore. I'm going to change this to this. Okay. Now we're going to talk about long-term capture rate and what that means. So it says a confidence interval gives us an interval of plausible values for a parameter. Notice they use that word a lot, which means it's important. Plausible values for a parameter. The interval is calculated from the sample data. So that means the interval is always going to be calculated based off of a simulation that is done or an experiment that is done. The confidence level C gives the long-term capture rate for calculating the confidence interval. What that means is that the confidence level of all possible samples is going to give us the most accurate interval to capture the true parameter value. So if we repeat this several of hundreds of thousands of times and calculate a confidence interval each time, our confidence level will capture the true parameter, and that is called long-term capture. Okay, so I would say if we repeat this process many times, calculate the confidence interval each time, it will capture the true parameter. That is called long-term capture rate. All of that is connected. Okay. And what you see is an actual diagram of what that would look like on the next part of the notes. Okay. So here you have a confidence level that consists of several confidence intervals. So if we were to say, if we were to create a confidence level based off of just our 3 periods, like my 3 periods of stats, I would technically only have 3 lines of data. But this has way more than 3 lines. So think of each line as a simulation like we did in class yesterday. So this is saying that if we took all of those confidence intervals, put it on one graph as a confidence level, we should see that 95% of all the intervals are going to correctly capture the population parameter of 0.7, which is what we were trying to find in our simulation yesterday. Okay. However, that means there's still room for error. 5% error could happen. And notice on mine how some of them are red. Those are the errors. When they did their simulation, okay, they got a value that was above 0.7. Okay, if we follow it down here, it looks like it's close to 0.9, like 0.87. Something around here. Okay. The next part says interpreting confidence interval and levels. Okay, all I want you to write here is that these are sentence stems. So you will use these for FRQs. Okay, I would just look over these sentences later on your own and understand which sentence is going to be used for a confidence interval versus a confidence level. So these are the sentence stems, and then the portion to the right of that is an example of how that would look like using our simulation data. So I would highlight it, box it, star it, whatever makes it easier for you to come back to your notes later. Be like, come back, see me, remember me. Okay. Okay, now we're going to look at the conditions for a confidence interval. What you should notice is that we're still using the same 3 conditions. We're still trying to prove if it's random, independent, and normal. So in order for us to prove that it's random, it's the same thing. We either are going to have a random sample, or if this was an experiment, it would be a random what? Assignment. Right, because in an experiment, you are assigned to a certain treatment. Okay, for independence, we are still checking the 10% condition. And to see if it's approximately normal, we're still going to check which condition? from the lab? Close, large, counts, condition. Okay. The only difference here is instead of saying n times p, we're going to say n times p hat. Because we are not given p. P is unknown. That is the actual proportion. We only have our estimated proportion. That's the main difference. Okay. And it says it right here. If you want to highlight that, we replace p with p hat. The resulting quantity is known as... I should probably say that first sentence. When calculating our standard deviation, because we do not know p, and we're replacing p with p hat, there is an error that can happen, right? Because when we did ours, we got 0.65 when it really was 0.7. So we had about a 5% error there. That error is called a standard error. It's denoted by SE, standard error. Okay. This describes how the sample proportion p hat will typically be to the population proportion p and related to SRS of a size n, so simple random sample. Meaning if we were to do this multiple times, we would expect this type of error. Okay, because they're not all going to be exact. It has its own formula. So standard error of p hat is equal to the square root of p hat times 1 minus p hat over n. Should look familiar, that formula. But before, when we talked about it, it was just p. And I do believe this is on the formula chart. Okay. Now it says calculating a confidence interval. So it says when conditions are met, the confidence interval for the unknown proportion p follows the following formula: p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Remember, this is our point estimate plus or minus our critical value times our standard error. So I'm not sure if it shows you exactly this on the formula chart, but it will show it to you in words. It will say point estimate plus or minus critical value times standard error. Because as we keep going through the units, the standard error and point estimate may change the formula. It's not always going to be that p hat times 1 minus p hat over n. This is called, so now we're getting to the big idea here. This is the inference name. One sample Z interval for proportion. Very important to not only understand how to use these inferences, but you have to know what they're called. Any questions so far? Okay, the last part of this note is going over an example of how an FRQ will look and everything that you need to include in it in order to get the full points. Okay, in the FRQs, remember you always have to use your 4 C's. And what are the 4 C's? Communicate. Conditions. Calculate. No. Conclusion or conclude. Okay? You need to memorize the 4 C's because it's not going to be set up nice and pretty like this on an FRQ. Okay, so the problem states, a recent survey wanted to see what proportion of high school students believe there is life on Mars. The poll's population was all American high school students. Okay, so this is like the name of their high school, all American high school students. They selected an SRS, that's important, of 430 students and found that 204 of them believe that there is life on Mars. construct and interpret a 96% confidence interval for the proportion of high school students who believe that there is life on Mars. So we sampled this one high school, the All-American High School, and we're going to see if we can use this data to make a bigger prediction of all high school students. So the first step is to communicate the parameter P in context of the problem. So we would say P is the proportion, and usually it's in the problem word for word. So proportion of high school students who believe that there is life on Mars. So of high school students who believe life on Mars. Okay. The next thing we're going to do is write down our confidence level. Okay, so that C percentage is equal to 96%. And now that we know the confidence level, we know the Z star value, which you can calculate using Desmos, and that gives us 2.06. And then the last thing from here is we need to find our P hat value. Remember, P hat is the proportion of this one high school. So they said, how many students believe? 204 out of how many students total? 430. So that gives us a P hat value of 0.474. So we're going to use this predicted value and see if we can create a confidence interval that says that about 47% of all high school students in the entire world, okay, believe that there's life on Mars. Okay, our next step is to check our conditions. So very important when you're checking conditions that you label which condition you're checking. Okay, the idea is to be as organized as possible so the grader can find your answer easy. So the first one says random. So in order to prove that it's random, we have to see what in our problem. That there's some type of random sample. Is there a word in the problem that shows that? SRS. So that's what we're writing. SRS, check mark. That's done. Okay, for independence, we had to use which formula? Or sorry, which condition? 10%. Okay, the 10% condition states that our sample size has to be less than or equal to 10% of our population size. Okay, so we would write that 430 students is less than 0.1% of all high school students. Would you say that this is a safe assumption? Yes, I would say there's more than 4,000 high school students in the entire world. So safe assumption, check mark. Okay, for normal, we have to use which condition? Large counts. So large counts. And then the only difference in the large counts formula is instead of P, we use P hat. So this is N times P hat. Who remembers the rest of the formula? Greater than or equal to 10. And the other one is N times 1 minus P hat, greater than or equal to 10. Okay, so plugging that in, this is 430 times 0.474 is greater than or equal to 10. I would say that's a good assumption because that's about half of 400, which is definitely greater than 10. And then 430 times 1 minus 0.474 is also greater than or equal to 10, which means that all those conditions are met. And once we know that all conditions are met, then we can actually start the calculation portion to solve the problem. Okay. For the calculation portion, it is not enough to write an answer. You will not get any points on the FRQ if you just write an answer. Okay? Because later I'm going to show you how to do this all on Desmos. So the first thing that you have to do is that you have to identify the inference method. Remember that thing I told you to star? What is the name of this inference method? Z interval for proportions. You need to write that out. That's 1 point. Okay. The next point you get is to actually write the formula. So that's p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. That's another point. The next point is plugging in the actual numbers. And then once you plug in the actual numbers, later I'm going to show you how to do this all on Desmos. So you're not going to have to actually do this math here. So I'm going to do that real quick for you. This is what you would get. And I'm going to write it in both forms. I'm going to write it using that plus or minus. And then I'm going to also write it with the interval because it wants us to find the interval. And it says there right at the bottom, find the interval. And how did I find this interval? Like, where did those numbers come from? Good, plus or minus the margin of error. Okay. So then the last thing I have to do is write my sentence using the sentence stem. So we say, we are 96% confident that the interval from 0.4244 to 0.5236 captures the true proportion of high school students who believe there is life on Mars. Meaning if we were to do this hundreds of thousands of times, 96% of all the simulations would find that between 42% and 52% of all high schoolers believe that there is life on Mars. Okay, and that's it for the notes.